Dr. Bean's playlist has the first video in here that goes through and explains a lot of different types of energy. You should consider watching it because it's really interesting. It really explains everything, especially about the microwaves, that first video especially. And then we have this playlist. This is going to be all the playlists for this chapter. And then we have the other YouTube videos. So these are just on all of the different topics, and it's a variety of other YouTubers that say things in really great ways. All different styles. So you can kind of pick someone and you can start searching on the internet for that topic and that YouTuber's name, and you should be able to find information. So let's look at electromagnetic radiation. It's a big long word, but that's what we're going to be doing some calculations with. So waves, like these kinds of waves, they have a magnetic component and an electrical component. In this list up here, Professor Dave has a fascinating video that shows how the waves look, the magnetic and the electrical components. They're kind of perpendicular to each other. And they make waves, they're oscillating movements. They transfer energy without transferring matter. That's what is different. Waves are not trying to transfer matter, at least not the waves we're talking about. So this is a scale that matches with this idea of increasing energy from the last video. And you'll notice that this scale uses nanometers for a while, and then it switches to centimeters. Remember, centimeters are several times larger. It's times 10 to the 7th larger than a nanometer. And then it jumps into meters. So you can kind of see the units on this are changing, and that these spacings that they're showing are actually much longer spacings than what's on this scale. And this section right here is the visible section. Visible light will fall into a range of, and this also is dependent on people, their eyes. If you've got someone who's really, really good at seeing colors, they may be able to see 400 up to 850. They may be able to see 850. Probably more people see in the range of 450 to 800. And again, this range over here, this is going to be the blue side of the spectrum, and this is going to be the red side of the spectrum, Roy G. Biv. So we're going to begin by doing some calculations, and then we're going to talk about why we're even doing these calculations when we're talking about electrons. So the rest of this video, we're going to look at the calculations, and then we're going to explain why we're even doing calculations and why we're talking about light when the chapter is supposed to be about electrons. All right, so we're going to use this equation first. It was what you saw before, to calculate the wavelength of light with a certain frequency. And the constant, it's on the previous page. Here it is again. So this is just a straight up plug it in kind of a situation. What do they want us to solve for? It says calculate the wavelength of the light. So this is what they want us to solve for. So you may want to go ahead and divide both sides by the frequency so that you're actually solving for what you want to solve for before you write all the numbers in. These numbers get longer and longer, so that it's just easier to move letters around. It's less time than moving 1, 2, 3, 4, 5, 6, 7 other things around. So just to help you practice using your E key, so this is like saying 3e to the 8th. That's the same thing as this, 3.00. You want to put the 00 in there. And then our frequency is this number over here, 4.28. And I'm going to use the E key here, E14. Now let's not lose our units because we want to show something that's going on with the units. So the unit for this is meters per second. The unit for this one is 1/seconds. So look, the same way that a meter over a meter, those cancel out, in the same way 1/second times 1/second cancels out. And the reason this happens, if you really want to follow it, it's like saying this, and remember, to solve a division fraction, you have to flip it so it becomes 1s times, and you invert it when you flip it. Now you can see that they cancel and become 1. And the reason I'm saying this is because this meters per second is the same thing as saying a meter times 1/second. So you can see that these units cancel. That's great because a meter is a length, which is what our wavelength is. And then we're going to pull over the calculator and put it on top of the screen. So we're going to say 3e8 divided by 4.28 e14. If you're not using the e key, you have to put parentheses around whatever's on the bottom of that denominator. So I get that the answer is 7 point. Now look, I've got 1, 2, 3 sig figs. I've got 3 up here too. It's a constant though, so the number that's on here, I'm going to write 1 extra decimal so that we can make sure about the rounding. And if I want 3 sig figs, it means that I need those 3, and we look 1 decimal over. Yes, that will round it, so that gives us 7.01 times 10 to the minus 7th meters. So we have 3 more questions here. In the same way that I solved this problem up here, you can solve this problem. I'm going to let you practice with that one. The h is given on the previous page. It's that 6.626 times 10 to the negative 34th. The unit is a joule times a second. That's important because we want the energy to turn out to be joules. And then we are going to, it says it's associated with the wavelength of light using the frequency in problem 1. So we're actually using the same exact frequency, and we're going to use it with this problem. And we're solving for E. So go ahead and practice that problem on your own. And I'm going to come back to this, but I just want to show you something that happens with our different equations. And I'm going to let you practice this problem and the previous problem. So you'll notice that some of these have similar components to them. I have a frequency and I have a frequency. I could substitute one equation into the other, but I need to rearrange it. And I guess which way you substitute depends on what you need. Let's go ahead and this time we'll solve for this, and we're going to substitute in to this equation. So we know that lambda times frequency is equal to the speed of light on the frequency by itself. So I'm going to divide both sides by lambda. So I get frequency is equal to c over lambda. Now I'm going to plug it into my other equation. E equals h times frequency. And I'm going to take this part and substitute in right there. So I get E equals h times c over lambda. And I can go ahead and extend that over, and that's fine. So now you can see that you actually have more than one equation. You have this equation, you have this equation, and you have this equation that you can use to solve things. So since you have 2 ways to get to E, how do you know which equation to use? Well, if they give you frequency, definitely use this equation because that's really easy. If they give you wavelength, you want to get this equation. But they are the same equation. Hopefully that you can see that the way we substitute everything in. So you're going to resolve problem 1, and now you're going to use this version of the equation, and hopefully you're going to get, it's actually question 2, but hopefully you're going to get the exact same answer. So on your own, work problem 2, work problem 4, and then I'm going to also let you work problem 5. This is going to be the same style of problems as the previous 2. There's one difference, and the difference is over here. They give you 95 megahertz. And frequency, to be able to use the equation, it needs to be in seconds to the minus 1 or hertz, which is the same thing as seconds to the minus 1. This one is a millihertz, not a megahertz. It's a millihertz. So it has to be in hertz before you can actually plug it into the equation. So remember, in 1 milli, there's 1 times 10 to the minus 3rd hertz. This is just like a millimeter versus a meter. It's just a unit is a hertz. So this is going to give us 95 times 10 to the minus 3rd hertz. And if you want to make that looking all nice, you can make it 9.5 times 10 to the minus 2. 1. And that's seconds to the minus 1, so that fits in really well.